If you take a water flosser and aim it at the back of a Lego car like this, the car should move, but the question is, how far? Welcome back to Engineered Bets. Today's line is 0.67 meters, and it's your job to take the over or the under. How on earth was the line set? Well, when I cranked the water flosser to its highest setting and measured the flow rate, I found that in 22 seconds it dispensed about 0.13 kilograms of water, which gets an average mass flow rate of 0.0061 kilograms per second. By looking at the jet, the diameter of the nozzle was estimated to be about 1 millimeter. Using this to get the cross-sectional area and assuming the standard density of water, you can solve for the exit velocity of the stream, assuming the flow is inviscid, meaning the velocity is the same throughout the cross-section. This gets an estimated exit velocity of 3.9 meters per second. I'll be attaching the water flosser to this wood block, and the key when attaching these clamps is you want to use a scuff drill bit and really rev the drill so you can completely strip the screw. Then when it inevitably isn't secured and aimed properly, you can have a fun time getting the screw out. Anyway, readjusting the setup and performing a test, the water flossers seem to shoot somewhat accurately, and I'll be aiming towards the center of the back of the car to the best of my ability, but I'll show you the setup up close right before so you can factor that in. The nozzle will be placed about 0.12 meters away from the car and will be launched from roughly horizontal at a height of 0.047 meters off the ground. I attached the wood backing to the car with hot glue to make the surface flat, and the bottom of this is 0.008 meters off the ground. Assuming the stream hits directly perpendicular on the back of the car and exits perfectly out the sides, the force exerted on the stream to deflect this flow was estimated using the very simplified form of the momentum equation, only looking in the horizontal direction. This equation ultimately came from Newton's second law, but I've chosen to just show the simplified end result for this idealized scenario just for the sake of time. Since this force acting on the stream will act equal and opposite on the car, this will be the propulsion force on the car. Assuming the car starts moving, I chose to estimate the rolling resistance using a coefficient of 0.0125, which is the midpoint of a range for an ordinary rubber tire listed on Wikipedia. And I'm sure by ordinary car tire, whoever added this probably was thinking about these wheels. Anyway, the last thing needed, the normal force of the car acting on the ground, is just equal to the weight of the car, which was found by measuring the mass of the car and multiplying by the acceleration due to gravity. This gets an approximate rolling resistance force of 0.008 newtons. To get how far the car should travel, there's two main phases I looked at. First, the acceleration of the car as the jet hits the back and pushes the car forward, and second, once the car travels far enough that it's no longer hit directly by the stream, the car will decelerate and coast to a stop. For the first phase, using Newton's second law, you can sum the forces and find the acceleration to be 0.235 meters per second squared. Even though the stream will drop as it gets further away and won't hit perpendicularly, it will be assumed that this acceleration is a constant for the full duration of this phase. Then for the second phase, the same is done, except now the only force is that rolling resistance, which slows down the car as it coasts to a stop, which gets you a deceleration of 0.122 meters per second squared. Assuming the jet trajectory will follow kinematics with constant acceleration due to gravity as done in previous episodes, you can solve for the time when the jet will no longer hit the wood panel on the back of the car. Using this time to see how far the stream has traveled horizontally, you get that the car will stop receiving propulsion from the jet 0.35 meters from the nozzle, or more importantly, 0.23 meters from the car's starting line. The car will accelerate at the constant rate found earlier for this first propulsion phase until it has traveled 0.23 meters. At this point in time, the car will have a velocity of 0.33 meters per second, which will be the initial velocity for the second phase where the car coasts to a stop. Using the constant deceleration found earlier, you can solve for the time when the velocity will reach zero, aka the car stops, and at this time the car will have traveled an additional 0.44 meters. Combining this distance with the distance traveled during the propulsion phase, and you see that the car should travel 0.67 meters from the starting line, and that's how the line was set. So in order for the over to hit, the back of the car must pass the beginning of this tape that I placed to be 0.67 meters from the start. Pause now to predict how reality will vary from this simple model, factoring in your own intuition and any assumptions you can think of that could lead to a deviation. I've set up the nozzle to try to shoot as straight as possible, but here's one final look at the exact setup from the side and from above so you can decide for yourself before I turn it on. Anyway, now it's time to see what actually happened. Turning on the flosser, and it seemed like some ignored static friction came to wreck the whole thing, but then suddenly the car shot off the line, although it didn't make it all the way. After further review, the stream hits the wood a bit to the right, which starts to move the car to the left, and then ultimately misses the car to the side somewhat early, meaning the alignment wasn't great, and I'm sure those of you who took the over are feeling a bit robbed right now. I'll be opening an investigation to see if it was rigged. If I placed the car slightly more to the right and angled it a bit, I was surprised to see how much further it could have gone, although the conditions were more slick during this later attempt. Anyway, since the car on the official trial did not move past the line, the under has hit. Congrats to those who got it right. Let me know in the comments which factors you think contributed the most to this result. Thanks for watching to the end, and I'll see you next time.